And basically, today is going to be kind of a warm-up for that, a little bit historical stuff, and then we're going to do a little bit of history, then we're going to do the Bohr model of the atom. Because later what you're going to do is solve the three-dimensional Schrodinger equation for the hydrogen atom. And some of the terminology from the Bohr model is relevant to that. And also the Bohr model is of historical interest because it was sort of the first hint that there might actually be like something to quantum mechanics. It was sort of the first tentative kind of feelings toward a quantum mechanical theory. And then we're going to do the three-dimensional infinite well, which is basically a three-dimensional box. And okay, so let's get started. I want to draw your attention to the Balmer series. In about 1885, Johannes Balmer noticed a pattern in visible light, which was basically what he was looking at the hydrogen spectrum. So you heat hydrogen gas, and he saw some sort of pattern. He saw various lines, okay? And they were, one of the reasons why he was able to work with this was because it was visible, okay? And he came up with an empirical formula to fit the four lines that he saw. And the formula looked like this. Lambda is B times m squared over m squared minus 4. And we have B is about, it's a constant, about 365 nanometers, and m is greater than 2. Okay, that's the Balmer formula, which basically he didn't have any sort of physical basis for it. He just noticed a pattern in these observations and figured out a formula that fit them. Then this was generalized by Rydberg. He wrote this in a new way. 1 over lambda is equal to r times 1 over n1 squared minus 1 over n2 squared, where n1 and n2 are integers greater than or equal to 1, and n2 is greater than n1, and r is a constant, which is called the Rydberg constant. Okay? So this would be used, basically this would be something you could measure, and then this formula turned out to fit all different sorts of hydrogen lines, visible light, not visible light. Basically what you had to do is you had to pick the n1 and the n2 right, and that would correspond to one of the seen lines in the spectrum. Okay? But there was no real, Balmer and Rydberg couldn't explain why we were seeing this pattern. Okay? And basically Bohr came up with a model that explained the pattern. Which, can you guess what his model is called? The Bohr model, right. Good. Paying attention. Okay, so the Bohr model of the atom, the basic ideas are that electrons are in orbits, and the angular momentum of the orbits is quantized. So by quantized means it can only come in certain chunks. Another way of saying is it depends on a quantum number. Okay. And so he wrote down the quantization condition as L equals NH bar. And there's basically, he didn't have a good reason. I don't believe he had a good reason for this. It was more in the nature of an inspired guess. The amazing thing is that it actually worked because his model is wrong. His idea was that electrons have classical orbits. So an electron goes around the atom, kind of like the Earth goes around the sun. And in fact, he had them going in circular orbits. And what we now know from quantum mechanics is that electrons don't behave like that at all. If a particle is in an orbit around a central body, then you are able to determine two things. You can say where it is and how fast it is going. Right? And we know from quantum mechanics that with an electron you can't do that. Okay? But the Bohr model preceded the Heisenberg's uncertainty principle. The Bohr model preceded the de Broglie hypothesis that physical particles have wavelengths. The Bohr model preceded basically all of quantum mechanics. The only thing that it basically came after was the explanation, the empirical fit to the black body spectrum that Planck did. You learned about that, right? You learned that Planck invented H-bar, basically, and the idea that the energy, if you have quantized oscillators emitting the radiation in a black body, then that would explain this black body curve that people were seeing. And it avoided the ultraviolet catastrophe. Okay? The next thing after that, which you've done also, was basically Einstein said that these photons are actually particles that actually have this amount of energy, and he explained the photoelectric effect, saying that photons are particles that have that can transfer exactly this amount of energy to a metal, to an electron in a metal, which kicks it out. And this is basically the next big step, the Bohr model in quantum. Unlike the photoelectric effect, unlike the black body radiation, though, it turned out that the model was incorrect. But it works surprisingly well. And some of the terminology survives, so I'm just going to quickly sketch out the argument. Okay? So if you apply F equals ma for a Coulomb force, okay, that means our force is equal to E squared over 4 pi epsilon naught r squared. And you use that the acceleration is v squared over r. This will lead you to, with a little bit of math, it's easy to do, that the energy in that system is E squared over 8 pi epsilon naught r. Okay, then you apply that quantization condition. Another way of writing this down, this is you're saying that the angular momentum, if you have a circular orbit, let me see if I can find a non-scratchy piece of chalk. All right, here we go, nice and soft. MVR is equal to, this is another way of saying that same thing. Okay, so you take this, does my V look too much like an R? Or can you tell them apart? Okay? Okay. You take that and you apply it to this relationship. So you basically have E squared over 4 pi epsilon naught. That's equal to mv squared over r. You take that, you feed it in there, and what you get out is you get out two things. You get r is equal to n naught a squared, n equals 1, 2, 3, so forth and so on, which is called the Bohr radius. Now it's mostly of historical interest, but this parameter a naught, which will be in this analysis, this will be the Bohr radius, the ground state. This parameter is important, and it turns up when you solve the full Schrodinger equation and find the actual three-dimensional wave functions and the energies of the real hydrogen atom. And the other thing that you get out of this is that E is minus 13.6 electron volts over n squared, so that the energy of the Bohr model is also quantized. And this turns out to be pretty much right. And I can't explain why it's right. There's probably an explanation somewhere of why it actually works. There's no reason why it should work because the model's basically wrong, but it does give the right answer. But then, let me see. Do I remember this? See if I can remember the... Oh, okay. Here, I can do something, a model that gives the right answer, but you can't trust, okay? It's an easy one you can understand. It's a way to divide, okay? 64 divided by 16. Now, my model is the cross out 6's rule. You cross out the 6's, that's equal to 4, right? Okay? So that model works in this instance, okay, but it's not a general... The model doesn't stand up to additional scrutiny. And sort of the Bohr model is kind of like that, okay? But the basic ideas do survive. The quantization of the angular momentum survives as a new rule. And I don't know if you're going to ever get to this, but if you do the path integral of p dot dr around an orbit, it turns out that is quantized and that survives. And as I said before, these energies are correct. And so you always, when you do if you don't include like relativistic corrections, if you don't have magnetic fields, if you don't have things like that, then this is the actual energy levels of the hydrogen atom. The other thing that this does not take into account is that the mass of the proton actually has a small effect on this. This energy, if you write out what the parameters are, depends on the mass of the electron, not the mass of the proton. The full expression depends on the mass of the proton as well. Okay. This thing n has a name. It's called the principal quantum number. And generally, when you're doing, and this survives to the full treatment of the hydrogen atom, n designates basically the energy level, okay? And so you'll always have, when you do the full one, your wave functions, your energy levels will include that designation. And one thing that you can do, and I erased the Rydberg formula, but if you take if you write this out, if instead of having the minus 13.6 electron volts, which is the reason why I write it down is I always remember that, and I don't remember all these other parameters. And you look at basically the model, which they go. Let me see. Let me try and draw this a little bit better. Here's the ground state. and then the next excited state might be up here, and then there's one here, and then they just start crowding up, okay? So here we have E equals 0, okay? So this one here would be the ground state, would be equal to minus 13.6 electron volts. And this here would be E2, which would be minus 13.6 electron volts divided by 4, right there, and so forth and so on. And one of the ideas that Bohr had, which was correct, is that what happens is if you have an electron transitioning from here, say, to here, then it gives off a photon, okay? And so you would say that because of energy conservation, the claim is that if you take the energy in this level, which let me call that E of N2, and I subtract the energy in this level, let me call that E sub N1, that is going to be hc over lambda, which is the energy of the photon. And if you rewrite these things, notice that we have the form, this gives me the 1 over lambda, and this is going to have the 1 over n squareds, okay, from the Rydberg formula. So if you rewrite this and put in all the parameters, this means that you can predict R, verify it. It's actually a post-diction, I guess, not a prediction. Okay? But anyways, you can calculate R based on fundamental parameters and see if that agrees with the measured value.
Is that an H?
Yeah.
Okay, so not.
That's correct, isn't it, for the energy of a photon? hc over lambda. Okay. Oh, one other thing about hc, since I briefly got on that. I believe that's 1240 electron volt nanometer. When you're doing atomic physics, that's a very useful number to remember because it comes up over and over again. And so instead of going through joules, because usually you're going to get these wavelengths will be in nanometers. These energies are going to be in electron volts. And so it's a lot easier to have this constant, which is the only thing left in here, that say might not be given. Say you have a 690 nanometer line, and you know the two energy levels, or you're trying to calculate one of the energy levels. It's a lot easier to do it using 1240 electron volt nanometers instead of going back and forth from joules and things like this. All right. So the other takeaway kind of thing is that the Bohr model, okay, is one of the first attempts at quantum mechanics. Part of it's right. The idea where you can quantize angular momentum. Of course, it's a more general form. It's kind of a path. It's used in a path integral formulation, which you probably never have to worry about. So maybe I shouldn't have told you that, but there may be some simple problems that we may use this formulation of Bohr's rule. And the other thing to remember is that the energy levels are right, and you should kind of know how those energies go. That is, I would definitely remember that they go like 1 over n squared, and of course it's a bound state. The energy is negative. After that, we want to sort of get started on the full 3D model and get to the model that replaced the Bohr model. Okay, the 3D Schrodinger equation. And I want to jump right to the time-independent version. Okay, this is the time-independent version. Which is the one that you usually do calculations using. at least that we do in the introductory course. If you're actually solving today's physics problems, you probably won't be using it very much. But when can I use the time-independent Schrodinger equation? There's a condition.
When the potentials don't change with respect to time.
Right. If I have a time-independent potential. So some of the things that are implied here is that I have U is equal to U of R. That is, it only depends on space. There's no time in there. And here I have psi is psi of R, some spatial function. And the energy is a constant for a particular wave function. Okay? And this thing here, this del squared is equal to d squared dx squared plus d squared dy squared plus d squared dz squared in Cartesian coordinates. Okay? You have different representations of del squared. When you write it down this way, you're basically writing it down in a coordinate independent way. That's why this is the best way to write it down. If your problem is simplest to do in Cartesian coordinates, then you'll use this version of del squared. When you do the full treatment of the hydrogen atom, it's simplest to solve that problem. It's probably impossible to solve that problem in Cartesian coordinates. But maybe I shouldn't say that because there may be a mathematician type here that will take it upon himself as a challenge to do it. So I won't say that. I'll say the problem is simplest in spherical coordinates. And so you would use the del squared operator written out in spherical coordinates when you do the full treatment of the hydrogen atom. So we'll go right to the reason why I brought up the Cartesian coordinates is I want to go right into an example, which we're just going to build on stuff that you've already seen. And I skipped over the part where you separate out here where you write the full wave function as psi of r and t, which is equal to phi of t times psi of r. Okay, that argument goes exactly the same argument that you did in 1D. Okay, where you have an e to the minus I e over h bar t, where you multiply to get the time dependent from the time independent, you just multiply by the phase factor. All that goes through the same. Okay, the infinite well is the 3D infinite well. Okay, it's best to just think of this thing as a box. So basically, you have a box, and you have a particle that's rattling around in your box, and the box can have different sizes for the distances between the various walls. Okay. So the potential is equal to 0 when 0 is less than L sub x, which is less than x. When 0 is less than L sub y. No. Totally messing that up, right? I guess I can write anything up here. X is between 0 and L sub x, y is between 0 and L sub y, and z is between L sub z and 0. Then the potential is 0. It's in the box. But the walls are impenetrable. You can't get through the walls. And basically the way that you say that is you say that the potential is infinite everywhere else. So there's no tunneling. It's trapped. Okay, then we do the standard thing. You write your psi of r is equal to f of x, g of y, h of z. Basically, it's a product of three independent functions, and the reason why you can separate this is that your potential has no functional dependence on x and z. If you x, y, or z. So if I had some u, say with some function of let's suppose that my potential was a function of f of x minus y, or maybe the absolute value of x minus y, some kind of weird potential. Okay, then you couldn't do this. You couldn't separate it. Would not separate because your x's and y's are tangled up with each other. They depend on each other. Okay, but if you have the case where it doesn't, where they're not like that, then you can assume that they're separable. And actually, in this case, it's the proof is in the pudding, because if you assume that it's separable and then you can solve it, then you're justified in assuming it's separable, weren't you? Right? And that's what we're going to do. And this part is basically exactly like the one-dimensional box, but let me just write the whole thing out in its full glory. Anyways, let's see. I want to keep my potential. Nah, I don't. Okay, so what you do is you put that wave function in the Schrodinger equation. So minus h bar squared over 2m del squared psi is equal to E psi. So we have minus h bar squared over 2m. How do I want to write this? D squared dx squared FGH plus d squared dy squared FGH plus d squared dz squared FGH is equal to E, and I'll put in the x's and y's just so it doesn't look so. F of x, g of y, and h of z. Okay? Does that look okay? Okay. So I just left out the specific variables here for the FGH. Then what you want to do is you want to do the usual trick. Let me save a little bit of extra board by, see, this is a function of x, but g and h are not. So I can take g of h, gh, and I can slide them through the derivative, right? And here, I can take out fh and slide them through the derivative, and that's just g of y. And over here, I can take fg and slide them through the derivative, and then I have h of z. Okay? So let's just rewrite that first line. And then you do the usual trick, and you multiply times 1 divided by FGH. This is the separation of variables. So then I have minus h bar squared over 2m, and that gets rid of that. So you have 1 over f, d squared f dx squared plus 1 over g, d squared g dy squared plus 1 over h d squared h dv squared is equal to E. That's legitimate, right? Okay with that? So basically what you have is, you have some variation here, plus some variation here, plus some variation here is equal to a constant. So by now this has got to be the second or third time you've heard this story, right? I mean, you heard this before for the when we derived the time independent Schrodinger equation from the time dependent one. There must have been some other time you had separation of variables, right? Or is this only the second time? Second time? Or first? Not the first time. Second time. Okay? If I can vary this, or vary this, or vary this, and in all cases this doesn't change, what can you tell me about these three things? Let me ask it this way. Let's write little f. Let's suppose I have f sub x plus little g sub y plus h sub z is equal to a constant. And I tell you that you can plug any z you want in here. You can plug any y you want in here. You can plug any f you want in here. And this equation holds true. Then what can you tell me about f of x, g of y, and h of z? They're constants, right? They're constants, right?
I was going to go with the inverse proportion. Like if you increase one, you decrease the other.
That won't work because I don't have to change z. I have the option to, right? So you might put in z equals 10, right? And I'm going to say, wait, I want z equals 100. And if that's the only change we make, this still stays this is still constant. So therefore, they're each individually constant. And that's basically the whole idea. And you're gonna see this story again when you do the three-dimensional Schrodinger equation. You'll see it again if you solve the Schrodinger equation in 2 dimensions. Okay, so you saw this breaking up the first time was going from time dependent to time independent. Okay, this happens again here, and whenever you have anytime you have the problem in many dimensions, you're always going to end up breaking it up in a similar fashion. You're always going to be separating the variables. And so basically, the next thing that you want to do is you write down something like d squared dx squared times f of x and some constant, let me call it c sub little x, times f sub x, okay? And so this c sub x would have something to do with the energy, something to do with h bar squared and the mass. You've seen this before, right? What was the system you saw this one in? Oh, 1D Schrodinger equation, yeah. Yeah, what was the physical system? You remember? No? Well, let me think. Wait, let me think. Maybe you might get something like this in a harmonic oscillator. Yeah. Do you?
I think you get a double.
No, I think you have a different sign somewhere. But you said the 1D infinite well? Yeah, this is the same differential equation you saw in the 1D infinite well. This is a 1D infinite well, which you've already done, okay? So you know that f sub x is going to be some a sine n pi x over L sub x. Okay? I can stick a little x on there. And you're going to get, you know, the same thing for the g, the same thing for the h, okay? We're going to have those functions that look exactly like this, because the potential, if you remember, our potential went from like between 0, x and L, and the same thing, y, z, okay? Where you had it was where you had zero potential. Just like in the 1D infinite well. So basically what I'm saying here is we're just going to reuse those solutions. You would go, if you wanted to sort of prove it, you would go through the same arguments that you did before. And then if you take these things and feed them, what we want to do is we want to take that and we want to feed it back into the Schrodinger equation. And I think that this is a good place to do that. Let me see. Let me get rid of this. You feed this back into the Schrodinger equation. You see, you are going to get, for this term, n sub x squared pi squared over L squared. Let me see, there's an h bar squared over 2m. Because when you do the sign, you take, when you take two derivatives of the sign, you get a negative sign. It's going to cancel that negative sign out. Okay? And we're going to have n sub y squared pi squared over L y squared. This is L sub x squared. And we're going to have n sub z squared pi squared over L sub z squared. And that's going to be E. And then you have three quantum numbers here, which you always get in three dimensions. N sub x, n sub y, n sub z. Okay? So we now have quantized our energy, and we have energy levels, and we have wave functions. Okay? And you can do this normal things like where you could normalize your wave function, and the whole wave function looks something like psi is equal to, no. We want to say if we're going to normalize, yeah, okay. Psi is going to be a sub x, if I write the whole thing out, a sub y, a sub z, sine n pi sub x, x over L sub x, so forth and so on. The part with the z and the part with the y, and you would say that 1 is equal to the integral over space of psi star psi. And here that integral would be dx dy dz. And you know, does anyone remember that for 1D, you had psi was equal to root 2 by L times the sine with all that stuff in there? Okay? So what do you think it's going to be? What do you think our full three-dimensional one's going to look like? Square root of 8 over L cubed, right? Pretty much. And if you do it, yes, it's going to work out that way. Because basically, what this is doing is you're basically doing one-dimensional integrals in three different directions. And you have the same functional form. So yeah, you're going to get the same thing. And it's going to be, it would be actually root 8, and you would get L sub x, L sub y, L sub z. And if all those lengths were the same, you get exactly what you said. We root 8 over L cubed, and then this will be times the sine, times the sine, times the sine, where there's the x part, the y part, and the z part. Okay? Total. What did I just flame? I think I was like hooked up. There's a speaker thing here. So Oh, here it is. Okay. It stayed attached to me. That's good. Now I want to ask you to make a prediction. So here you have two things that you get out of this. Okay, you get the energy levels with the quantum numbers. Those are the n's, and you get the wave functions, the size, which is going to be, in this case, it's a product of three signs, one in each dimension. Okay, I would like you to write down for me. Let's do the two-dimensional well problem in our heads. How many quantum numbers am I going to have? 2. Let's call them n sub x and n sub y. Okay? So my energies are going to be h bar squared over 2m. Wait, someone's saying this all right. Who's saying it? Who's got it? Say it loud enough so I can hear you.
Times the quantity of nx squared pi squared over ly squared plus ny squared pi squared over ly squared.
Exactly. Okay? So and so you could write down, in principle, you could write down the energy levels for a 8-dimensional box, right? An 8-dimensional infinite box. Okay? You know, basically, since you know how to do it in one dimension, and you've done it in more than one dimensions, and you see what happens, you see that there's a pattern there. And so now you could basically write down the energy levels for any dimensional box. I mean, physically, we can only make, you can make systems that sort of, that will simulate, that would behave like a one-dimensional box. I think those are called quantum dots or something. Is it, I don't know. I don't know anything about quantum dots. It may or may not be a quantum dot. You can have systems, you can create physical systems in the lab that would simulate a two-dimensional well. And of course, you have the three-dimensional well, which is just like a box. If you were interested in doing physics in a universe that had more than 3 spatial dimensions, okay, and the Schrodinger equation applied in that universe, you now know how to solve the n-dimensional Schrodinger equation, okay, for the infinite well, which is particularly simple. But you could just write that down, and you could also tell me the wave functions, couldn't you? You could, right? It would be 2 by L times product of sines, right? You'd have the sine in the x direction, you'd have the sinusoidal in the y direction, and you'd have some normalization factor out in front, which would look exactly like the one that we have. It's basically just this root 2 by L kind of thing to the appropriate number of dimensions. Now there's something else though that's changed, okay? One of the other things that you do, and you'll often be asked to do when you're doing quantum mechanics problems, is to determine the ground state. We're always interested in the ground state energy. And this will come into play a lot when you do statistical mechanics, okay? Because the ground state, most things like to sort of be like settled and comfortable, right? They want to like be in the basement, where it's warm, okay? So systems of particles tend to live in the ground state. So you could say that the ground state of a system is its most important state. Okay. Now here you can actually easily find the ground state. If we set n sub x equal 1, if we set n sub y equal 1, if we set n sub z equal 1, obviously that's the minimum, because what you're really interested in is the sum of the squares of those integers. And who knows, maybe you could come up with some spectacular combination of L's that would make that wrong. But I think that probably no matter what I pick these L's to be, I would all have to set n sub x, n sub y, and n sub z equal to 1. Okay? Now the next important state after the ground state is basically any excited state, because those excited states are involved in transitions. So when you're putting energy into or taking energy out of a system, there's a transition involved. So your system will go from the ground state to an excited state. If it's absorbing energy, it will go from an excited state either to another excited state or the ground state if it's emitting energy. And so you need to know about these energy levels. And it actually turns out to be important how many energy levels there are that have the same energy. When you go on and do like statistical physics, if you want to figure out how a white dwarf star works, for example, that turns out to be very important. An easy way to basically see this is if we set, or an easy way to kind of look at the phenomena of degeneracy. Degeneracy, which means if you have different quantum numbers but the same energy, then that energy level is said to be degenerate. Well, if you do an example, if you set those three guys equal, then you basically have h bar squared over 2m L squared times nx squared plus ny squared plus nz squared is equal to E, okay? And now obviously you have obvious degenerate states, like if I set n equals 1, n sub y equals 2, and n sub z equals 1, and I compare that to 1, 1, 2, and I compare that to 2, 1, 1, okay? If I look at these three sets of states where I've basically, let me write it maybe this way. Put some commas and some brackets in there. So I'm just identifying, the thing in quantum mechanics is basically, if you specify the quantum numbers for a system that has known energy levels and known wave functions, you've specified everything about the state, okay? And so I'm just listing down these quantum numbers as in x, y, and z, okay? And so you can obviously see if you look at that, if one of them is 2 and the others are 1, it's going to sum up to be the same, so you're going to have the same energy. So those three energy levels are degenerate. Oh, I found a curious one. I wonder if I wrote it down here. Oh, okay. This is also degenerate for this system. 3, 3, 3, and 5, 1, 1. Right? 3 squared plus 3 squared plus 3 squared is 27, right? 5 squared plus 1, 27, okay? And so this state is degenerate with this state, and it's unlike this in that you're not just sort of moving them around, but these are actually different energy levels that are involved. Sometimes that's something that it could potentially trip you up in certain types of problems where you had to count the states that were at certain energy levels in order to figure out how the system would spread itself among those various states. I just want to say that, trust me, okay, that this concept of degeneracy is extremely important, okay? Trust me on that. One other thing is that the last thing I want to say about this is that the Bohr model doesn't have this. Okay? When you do the full, it can't because it's basically a one-dimensional model. Even though it's a circle, the Bohr model is basically a one-dimensional model. There's one parameter in it. Okay? When you do the full treatment of the Schrodinger equation for the 3D hydrogen atom, you will have degeneracies. That is all I want to say. See you tomorrow at 10 if you choose to go to the morning recitation.